Hi everyone, this is Emrah Turgut. Today we will continue chapter 22. So before starting, I would like to make some announcements. I'm sorry I'm slow in responding your emails. I just got the spreadsheet from the CHAG and I will see and then find the corresponding emails and etc. Sorry it takes some time, but I will sort it out. So let's get started for the chapter 22, lecture 2. So you may notice that my screen shows the different dates. That's kind of funny. Whenever I connect my iPad to the Zoom, it doesn't read the current date and time. Anyway, so last lecture we learned about force on electric charge moving in a magnetic field. So we will continue on this subject because we will see some applications and build in like the following topics on this. What you need to remember, you have three things. First, the magnetic force is perpendicular to the magnetic field direction. The force is perpendicular to the magnetic field and the velocity. Second, you will use right-hand rule to find the direction. And third, the equation gives the magnitudes. And then by looking at this force on the particle, we will learn about cyclotron motion, mass spectrometer, Hall effect, force on a current carrying wire, torque on a current carrying wire. So we don't maybe see that in the everyday, but these are very important topics and be useful in many different technologies. So one thing is the cyclotron motion, which happens when you have a charge particle moving in a magnetic field. So it makes a circular motion because when you think the force is always to the center and the perpendicular to the velocity. So let's say you have a rope and you have a rock at the end, and you do the rotation like this. So you have a circular motion of the rock, but what happens, the force is always along the rope, right? It's always to the center when you have a rope at the center, and the velocity of the particle is always perpendicular to the rope. So they're the same like analogy, like you have a force coming from the magnetic field and it always points to the center and perpendicular to the velocity. So it forces the particle to have a circular motion with the same speed, just the vector of the velocity changes and it will go on the circle. And the magnetic force is given by QVB. Q is the charge, V is the velocity, B is the magnetic field. And it's gonna be equal to the centripetal force, which is mv squared divided by the radius. I hope you remember from the physics one. From this, you can calculate the R. R is going to be m times velocity, m is the mass. So you divide by QP. Then we have a cyclotron frequency, which gives the angular frequency, angular speed of the particle, and which is going to be velocity divided by R, and it is given by QB divided by M. So this case is true when the velocity is perpendicular to the magnetic field, which means that the angle between them is 90 degrees. That's what you see here. The magnetic field is going into the page. And the velocity when it enters, or anytime it's on the plane, so it's always perpendicular. If you have a component of a velocity parallel or in the same direction, parallel to the magnetic field, that component of the velocity will not change. For example, you have a Q charge and you have a magnetic field along the x-axis. And you have a magnetic velocity, we call it V parallel to B. And you have a perpendicular one. And this perpendicular velocity is going to be what you see changing in a direction, but the V parallel is not going to change because there is no force along that way. So what's going to happen is the particle is going to do the cyclotron motion perpendicular to the V, and it will do some propagation with the parallel velocity. So a magnetron in a microwave oven emits microwave with frequency of 2450 megahertz. What magnetic field strength would be required for electrons to move in the circular path with this frequency? So this is a frequency, not the angular frequency. Normal frequency, which means that the inverse of the period, right? So the period. What's the period? It's 2πr is the circumference, and you divide by the velocity, right? And actually this is 2 pi V divided by r, and the angular velocity is going to be V divided by r. Let me remind of this one. V divided by r. So it's a QB divided by m. So it's going to be 2 pi divided by omega. And omega is QB divided by m. So you can derive the equation if you want, like QVB equals mv squared divided by r. So you can cancel one velocity and you will have v over the r here will be equal to the qb divided by m. So you can get the same thing. So the q, okay, let's find, it asks about the b. Let's plug into the omega here. So f, the frequency is 1 over t. 1 over t is going to be omega divided by 2 pi, right? For omega, I will write q b divided by m, 2 pi. So the b, the magnetic field, is going to be F times mass times 2 pi divided by q. F is 2450 megahertz, 10 to the 6 hertz. The hertz, by the way, is the hertz is the unit of frequency, and is 1 over second in terms of unit, because the period is in terms of second. So this is F. Mass is 9.1 10 to minus 31 kilogram. It's the mass of electron, and you have 2 pi. And the charge is going to 1.6 10 to minus 19. So if you calculate 50 times 9.1 times 2 times pi divided by 1.6. So it's going to be, write it here, 87 552. And let's calculate the exponential. 10 to the 6 minus 31. It's going to be plus 19 when you bring it to the numerator. So then it will be minus 25 and minus 6. It's 10 to minus 6. Tesla is going to be 7 Tesla. About 87 millitesla. If you open in the microwave, you can see this permanent magnets that creates them much magnetic field. Indeed. Okay, this is how we approach the problem and solve it. The mass spectrometer is the second example we will talk about. And it's actually very, very important in biochemistry. What you have in the mass spectrometer, first you have a magnetic field and electric field that picks the velocity of the particle. Then it enters in a magnetic field medium. So this is the second medium, which has only magnetic field. And then the particle is moving in a circular motion, a cyclotron motion, but it hits the detector. And by looking at where it hits, you can determine the mass because the radius of the motion is going to depend on the mass. The first part is you must know the velocity. So in the equation you have V. So that's why you have this first part, electric and magnetic field determines the velocity of the particle. And from the velocity, you have the electric force will be equal to magnetic force, right? So electric force is Q times E, and the force of the magnetic field is QVB. So the velocity is electric field divided by magnetic field. So in one problem here, we have two masses and we have a detector. So now it asks about the angle, but let's anyway, this is the center, so it makes this circular motion. So let's find the differences between the two radiuses, R1 and R2. So R is mv divided by qb. So indeed, it doesn't show the charge, but when the, let's say, is on the one, like a positive charge, let's say it has excessive less, let's say it doesn't have, it has a less, one electron less. So the charge is a positive, so one more proton. So R1, 2 is going to M12 velocity Q divided by B. R13 is M13 velocity Q divided by B. So R12 equals mass 1.99 10 to 26. Velocity is 5 times 10 to the 3 meter per second. Q is, let's say, 1 excessive photon, minus 19, and the B is 0.01 Tesla. Then the radius is going to be 0.99 times 5 divided by 1.6. It's going to be 622, and you have 10 to the minus 26 plus 3 plus 19 and plus 2. And you have 5, 4 and minus 2 meters. 413, we'll just use the mass 2.16. So it's going to be 675 meters. It's about centimeter. So the first radius is 6.22 centimeters. Second one is 675 centimeters. So it's about 5 millimeter displacement or distance between two radiuses. The Hall effect, when a current carrying conductor is placed in a magnetic field and the particle, you can think electrons are moving, and they will be force perpendicular to velocity, which is current, and the magnetic field, and that will create the separation of electrons in the one side and the positive charges at the another side. So that will be a perpendicular voltage, perpendicular to current and the magnetic field. So we call it Hall effect. So this is a super useful measurement to determine the carrier concentration, and you can use as a magnetic field sensor, and etc. So let's try to understand this. Let's say you have the film. I'm imagining as a three-dimensional slab. So you have a current, and let's say you apply a magnetic field perpendicular out of, say, that perpendicular direction. So if the current is moving that direction, the electrons are going to move into opposite direction, right? So the magnetic field will create a force for, let's say, for the force on the electric field on electron. Let's find it. And the first, you will just imagine you put your fingers along the velocity, right? You have your fingers, and the magnetic field is going to be the palm, right? And when you put the force, so force is going to be up, but for the positive charge. But the electron is negative, so the force must be the opposite direction. So force is going to be this way. So again, the force is perpendicular to B and I. And as you pass the current, what's going to happen here is the electrons are going to come this side, right? Because there is a force pushing them that way. On the other hand, you will have positive charges at the other side. So this will create some Hall voltage or Hall electric field. You can call it electric field or Hall voltage, and you can measure this voltage by using a voltmeter connecting these two ends. The most important thing is that the Hall effect is perpendicular to magnetic field and the current. And the Hall effect distance, the velocity, you need to know the drift velocity of the electron for this, and it's related to the current. So if you remember, current was in Q S, and S or area, We'll put an area, and the drift velocity. So for the drift velocity, you can I divided by NQA. Here the T is the thickness. So because say delta V is the Hall voltage, depends on the electric field times distance. This distance, then electric field is going to be in the balance, right? Like a mass spectrometer. And you can write drift velocity times magnetic field. And drift velocity is written by, in terms of current, so you can measure the current, I, N, Q area. And you have magnetic field and D. And if you look at the area, call it this T thickness, T times D, right? For area, you can write T times D, so you can cancel the D's, and the whole voltage is going to be IB, and you have NQT. So that sometimes we call this Hall coefficient 1 over NQ. That gives the concentration. So that's one of the ways to measure this concentration. Now we will move on the force on an electric current in a magnetic field. Indeed, any current is a moving charge. You can imagine the magnetic field applies forces on individual charges, each individual charges in a wire when they move. So then we can define this current as the force as a whole, total net force on the wire. Then the force on a wire is going to given by Fi, the amplitude of the current, times length of the wire and the magnetic field. And again, we will have the sine theta function, the term, and it's gonna be perpendicular component of the magnetic field, or you can also call the perpendicular component of the current. And we will have the right-hand rule again. So let's say you have a magnetic field along this direction, and you can split the magnetic field into two, which is perpendicular component, P sine phi, and the parallel component, P parallel is cosine phi. And the parallel component is going to apply in the force. The only perpendicular component is going to do it. And here you can write the force IL P sine phi. So here in terms of units, force is Newton, I is ampere per second, and the L, the current is ampere, which is coulomb per second. The L is distance, meter, B is Tesla, magnetic field. So there are a couple of examples like to how you can calculate the force and just the kind of problem to understand this concept. So you have a rail gun, and this is the first problem, and you have a conducting bar, and when you put a battery, so it's asking which orientation we should put, the bar is gonna go to the right, and with the magnetic force is going to be the right. So I'll ask which orientation we should connect the battery. Actually, the first you need to understand the direction, or you need to find the direction of the current. So to be able to such current, we need to find you need to use the right-hand rule. So you can make some, let's say if the current is this direction, so the magnetic field is into the page. So I, B, but the force is going to be opposite to the left, so which is wrong. So then what should happen is the current should be down. When you put the current along with your fingers and find the magnetic field with your palm, and it's going to show the force. So this is finger and the palm into the page. That's the magnetic field. Then the force is going to be right to be able to have such current going through this way. So you need to have a positive this side and the negative this side. So the orientation should be this one. And you have another problem. So you have a bird, and we would like to suspend the bird in an air by the magnetic field. So you have a mass of the bird, 1.6 grams, and the wire is 10 centimeters long and the mass of 7 grams. Then you pass 4 amps. So what's the direction and the magnitude of the magnetic field? So the force, total force, is going to be mass of bird and mass of wire, Ng. So that will balance by the magnetic force, right? I, L, B. So the bird mass, let me add a page here. So the 1.6 plus 7 grams, 10 to the minus 6, minus 3, which means kilogram. G is 10, right? So I'm making as a Newton. So the force I, LV, I is 4 amp. Distance is 10 centimeters, so it's gonna be 0.1 meters. Times V, that's what I'm looking for. Then you have 8.6, 10 to minus 2, divided by 0.4. It's gonna give the magnetic field. So it's going to be 215 and 10 to minus 1. 0.50 Tesla. So in terms of direction, let's find if the current goes this way, the magnetic force should be up. So you put the finger along the current, and the force is going to be up. So the palm should show the magnetic field, and the magnetic field gonna be into the page. Into the page. So this is the eye. Right. So another application of this force is a motor, which converts the electric energy into the mechanical energy. So what you do is you make a loop. I'm sure you open the end inside of the loop motor. You have wrappings of the wires, and there are 2 magnets, like perpendicular permanent magnets, and creating magnetic fields. And as you when you pass the current, it will apply the torque to the wires and it will rotate. And the torque is given by N is the number of reps, because each loop is gonna create the force. So you will have this number of reps, current, and the area of the loop, and you have the magnetic field. And the angle is going to be this angle. The torque is going to depend on that angle. So this Ni times A, which is going to be the number of reps, current, and area is going to called magnetic dipole moment, which is kind of the independent of the magnetic field and angle, just to define the property of that loop or the reps of the wires. So we call magnetic moment. Okay, so this is all about the current for the motor. And what you need to is you create torque, and torque is given by this equation. So we will not derive it. So what you need to remember is depends on the number of reps, current, area, magnetic field, and angle. So let's solve some examples. You have ABC particles. What are the signs of the charges on the particles when they move along with this paths in a magnetic field going into the page? So let's say for the A, you have velocity. Put your finger along the velocity and you will find a magnetic field. And the force is going to be this way, I assuming at a positive charge. So A is positive. So the C will have the opposite force, which means it's negative. B doesn't have any force, but it moves, which means this is neutral. So question, which of the particles in figure has the greatest velocity, assuming they have identical charges and masses? So two particles, A and B, are moving in the cyclotron motion, and one has a larger radius, other one is smaller. So which one has a greater velocity? And we are assuming they have same charge and mass. So you can drive this mv square, centripetal force, equals qvb. Then you have mv. Now I will leave the reduce on the right hand side. I will divide qb r. So do you assume that, think about it, the mass and charges are the same. So, oops. So this is the same, this is same. So magnetic field is same. So what you have is velocity and r, and they are proportional, linearly proportional. So when you have a larger radius, in case RA, which means that the velocity of A is going to be larger than velocity B. Now we have four charges in the next question, A, B, C, D, and moving in the XY plane is showing, the velocities are shown here. Rank the charges by the magnitude of the magnetic force exerted on them from largest to smallest. So let's find the forces on each, and for A you have Q, V naught, Q naught, and B, and the angle is 90 degrees between the magnetic field and the velocity. Sine 90 is going to be 1, right? So FB is going to Q naught, 2V naught, because the velocity is 2V, and B sine 90. FC, you have 2Q and 2 velocity, and B, and the now angle is sine 45. And FD is Q naught, 3V naught, B, but the angle is 0, sine 0. So the force is going to be 0 on D. So, okay. Then FD is smallest. Let's find the sine, find the 1. This is 1 over square root of 2. So FA is QVB, 1 unit. And the FB is 2 unit QVB. FC is going to be 2 divided by square root of 2, 2 square root of 2 QVB. So FD is 0. So the largest is C, then B and A and D. That's all for this lecture 2, and you can see some summaries here. We talk about cyclotron motion, mass spectrometer, Hall effect, force on current carrying wire, and the torque on a current carrying wire. So see you next time at lecture 3.